Hello, class. This is Mr. Hart, and in this podcast, we want to continue our chapter on dating techniques. And so, we've spent a lot of time talking about relative dating. In this podcast, we want to look at absolute dating, or often what we call radiometric dating. Okay. So, when we do radiometric dating, what we're doing is we're measuring the radiation of an object to determine its age. Okay. So, every object's going to have certain materials inside of it that are going to be radioactive in some way. And based on how much radiation we can see coming from these materials, we can determine how old they are. Okay, this will make a little bit more sense in a second, but one of those materials is actually a mineral called zircon. So certain rocks and things like that will have this zircon mineral in it, and based off the radiation coming off that mineral, we can determine how old the rock is based on the mineral's age. Okay, so it's not like relative dating because we're not comparing it to anything else. We're just using a feature of that material, its radiation, in order to determine how old it is. Okay. And so in order to do that, we use a process called half-life. Okay. And so what a half-life is, it's the time it takes for half of the radioactive material to decay. So let's say you have some type of radioactive material, okay, and right when it's formed, that material is 100% radioactive. Over time, it's slowly going to lose that radioactive material and decay into something that is stable. So this blue line represents the radioactive material, or what we call the parent isotope. And this red line represents the non-radioactive material it decays into, the daughter isotope. Okay, so let's focus on the blue line, though, the radioactive material. So after a certain amount of time, okay, you start losing radioactive material because it's giving off radiation. And it'll reach this point where half of the material has only half the material is radioactive at this point. Okay, so we call that time one half-life. Okay, so if we wait one half-life, only half of our material will be radioactive. Okay, if we wait another half-life, then only a fourth will be radioactive because that's a half times a half. We wait another half-life, then only an eighth of it will be radioactive. A half times a half times a half, and so on. And this would be 1/16th. And if we waited another half-life, it would be 1/32nd. Okay, so just based on how much of the material is radioactive compared to how much should be radioactive, we can figure out how old that object must be. Okay, so this is what we call a half-life. Okay, and I use that to determine the age of objects. Okay, in a process we call radiometric dating. Okay, so we watched this video on YouTube about radiometric dating. Okay, and this guy in New Zealand, he actually takes a rock sample and he shows you how they take those minerals and the zircon and things like that, and they can actually separate the radioactive material from the non-radioactive material. Okay, and so if you watch that video right here, you'll see them use that machine, use the process to separate the two so they can determine how old it is. Okay. We also used a simulation, a PhET simulation, which you can look up on the PhET website. Okay, and it shows how if you use different minerals and different materials like carbon-14 or uranium-238, they have different half-lives. And so using those different materials, you can determine how old the certain objects need to be. Okay? And we also did a lab in class, which we call the candy lab, where we took some Skittles and we pretended like they were radioactive, and we saw how over time the number of radioactive Skittles decays or goes down over time. Okay, so we did a lot of things in class, and hopefully you can kind of understand how these certain things work as we go through. Okay, but if you want some more help, definitely go back to these other resources and look at those. Okay, so let's look at another application of radiometric dating. So we can not only can we date like rocks and minerals, but we can also date things like cave paintings. Okay, so this cave painting was determined to be 27,000 years old because they looked at the ash or charcoal or whatever they used to make the drawing, and they can actually measure the radiation coming off of that painting. And so they use radiometric dating to determine the age of these objects. So this is really cool. So not only can we do rock layers and things like that, but we can do paintings, fossils, artifacts, things like that as well with radiometric dating. So there's lots of cool applications to this as well. Okay? All right, so let's look at how we actually calculate the age of an object using half-life. Okay? So there's actually a much more complex version using exponents and things like that, but this is the simplified version that we need to know and understand for 8th grade science. Okay, so the age of an object, which we'll call t, time t, the age of an object is equal to the number of half-lives that have occurred, n, times, this is a times sign, the length of a half-life. So in order to find the age of the object, we just find how many half-lives have occurred and times it by the length of a half-life for that object. Okay? And you can write whatever variables you want. These are kind of just the ones I have written down, but if you want to write down other letters to help you make more sense, that's fine. But as long as you get this idea, number of half-lives times the length of a half-life gives us the age. Okay? So if I have something that has had 4 half-lives occur and a half-life is 5,000 years, then that object must be 2,000 or 20,000 years old. Okay? So let's look at how we find out the number of half-lives. Okay, so this is an example we did in class where I said I have a 40-gram sample, but only 5 grams are radioactive. Okay, so if I have a 40-gram sample, only 5 grams are radioactive, then what I do is I need to figure out how many half-lives have occurred. Okay, so if 40 grams is my starting amount, then after 1 half-life, 20 grams will be available. After 2 half-lives, 10 grams will be available or radioactive. And then after 3 half-lives, 5 grams will be radioactive. So I just keep dividing by 2, divide by 2, divide by 2. This means that 5 grams matches 5 grams. That means 3 half-lives have occurred. Okay? So if I have a 40-gram sample and only 5 are radioactive, then I just divide by half, divide by half, divide by half until I get to the number I have. That's how many half-lives have occurred. Okay? And then what I do is I say, well, that's the number of half-lives, and let's say the half-life length is 10,000 years or something like that. Then we must know that 3 times 10,000, and we know that the age of this object must be 30,000. Okay. All right. Simple enough. Hopefully that makes sense. Let's try one more example. Okay. So we have a carbon-14 sample that has a half-life of 5,000 years. Okay. So if it has a half-life of 5,000 years, okay, and there's a 10 kilogram sample and only 2.5 grams are radioactive, how old must it be? Okay. So we say we have 10 kilograms to start with. Well, if we divide 10 kilograms by 2, we get 5. And if we divide 5 by 2, we get 2.5. Okay? And there we go. That matches our sample. So that means 1, 2 half-lives have occurred. Okay, so n equals 2. And we know that the half-life length is 5,000 years. So it's very simple. We just take n equals 2 times it by 5,000. That gives us that the age of this object must be 10,000 years old. Okay? And there you go. So fairly simple process. Hopefully that makes sense, but that's the other method other than relative dating. We have absolute dating or radiometric dating. This is the other method we use for determining the age of objects. Okay? So there you go. Relative dating, absolute dating. Now we can kind of give a good idea of how old any object is using one of those two methods. Okay? But let me know if you have any questions, and thank you for watching.